Hello everybody, I'm Incho from Cloud Database team at Tencent. Today is my honor to talk about the story with respect to the evolution of Tencent's database technologies. Here's the agenda of today's talk. The talk will start with a brief introduction to Tencent's TD-SQL database products, and then with a focus on the cloud-native database TD-SQL-C, I will talk about the innovations we have made on the architecture, as well as the key technologies that has been implemented to resolve the challenges we met. Finally, the talk will end with discussions on the future work. Okay, start with the introduction about the products. Nowadays, a database plays very important role in mission-critical applications. Tencent keeps investing on the research and development of a variety of database products. TD-SQL is a unified brand representing a product matrix which consists of most very important products in Tencent for OLTP and OLAP respectively. On the left side are three OLTP products: Enterprise MySQL, formerly called CDB, is Tencent's RDS systems, which are enhanced with a lot of patches, optimizations, and enterprise-level features. For example, the SQL audit, the database encryption, and firewalls, so on and so forth. In the cloud-native database side, we built TD-SQL-C. It's a shared storage product with decoupled computing and storage layers. It has two flavors. One is for MySQL and the other one is for the Postgres. We also have another MySQL compatible product, TD-SQL. It's based on share-nothing architecture and is best used in the case with a very large amount of data. For analytical workload, there's another OLTP product, TD-SQL-A, as shown on the right side. It's a shared-nothing MPP database supporting columnar storage functionality and also provide Oracle compatibility. Let's take a look at the scaling and the user case for the TD-SQL products. TD-SQL products are widely used across different areas, covering e-commerce, finance, social network, entertainment, videos, and so on. Here, we only list the typical users for each individual area. Right now, there are over 1 million CPU cores deployed on the Tencent cloud for database instances, with more than 100 petabytes billing storage. We can say for some internal customers like the WeChat Pay, and also the game team for the very popular game. So given today's talk, given the limited time of today's talk, it's not possible to cover every one of the products today. So next, I will mainly focus on TD-SQL-C, one of the cloud-native database systems. Let me start with the architecture of the TD-SQL-C. Before that, I need to mention the challenge we met before we make the change to the architecture. As you know, cloud-native is essentially a set of concepts and technologies that leverage the cloud infrastructure to provide a cost-efficient and highly available solution to the customer. It's also true for a database and cloud-native context. So we want to make sure what's the problem with the current MySQL database architecture, and what are the challenges right there that we have to resolve in order to build a cloud-native database. So let's say in a traditional MySQL cluster, whenever one node joins to the cluster, it has to create a copy of exactly the same data at the local storage. Generally speaking, When deploy a slave instance, the bigger the database is, the longer it takes to bring up the instance. Also, it incurs the redundant storage consumption, which is not necessary and to some extent a kind of waste. So let's do the math. For a database with 1 terabyte data, a cluster with 1 master and 3 slave nodes will totally occupy about 4 terabytes storage space. Also, once the limitation of storage capacity on one machine is hit, the database instance has to be migrated to a large size node. The process is pretty complicated and time-consuming. Reliability and availability-wise, data loss could happen with synchronized replication. Synchronized replication is safer, but the latency is much higher. Also, it might take longer time to recover from a failure and HA switch, negatively affecting the system availability. Last but not least, tightly coupled computing and storage layers may cause some suboptimal hardware resource utilization. For example, you can imagine a scenario where the disk is almost full, but the CPU usage during the ordinary time is pretty low. For the storage purpose, you have to migrate to a big size machine. A large size machine generally configured with much high-end CPU resources. This means the customer has to pay more for unused CPU in most of the time, which is not cost efficient for the customers on the cloud. So in order to resolve the problem mentioned before, we need to make some fundamental change to the architecture. Let's take a look at the new architecture of our cloud-native database TD-SQL-C, formerly called SinosDB. There are still 1 master and multiple slave nodes there, but the biggest change is that the computing and storage layers are decoupled right now. Instead of replicating to the slave node by the binlog in the classical MySQL cluster, TD-SQL-C replicates by the read log, which represents how data page is changed, and the performance is much better compared with the original one. We also implement a couple of concepts like logis database. The master node at the computing layer generates the redo log and offloads the redo log to the storage layer. It's storage layer's responsibility to take care of redo log replay and the dirty page flushes. This makes the computing layer lightweight and stateless, which is very convenient for instance to start up and shut down, as well as the cluster scaling up and down. At the storage layer, data is split to small pieces of segments that are organized to a set of cells. The log is dispatched to the page of specific segments so that different pages can apply the logs in parallel. Data are saved and retrieved through the database-aware interface to talk to HiStore, a generic high-performance block storage system. Its I/O latency is as low as only 40 microseconds. HiStore provides a very solid basis for different upper-layer applications by different interfaces. The data is kept with multiple replicas to ensure high availability. When there is a need to bring up a new slave instance, it only reads necessary information from the shared storage and don't need to maintain its own data copy in the local disk. It reads data from the storage layer only when there is a cache miss. The redo log received from master node is is used to update the slave's local buffer pool. The process to bring up an instance is much faster than before. With multiple nodes sharing the same copy of data, storage cost is significantly reduced. The benefit of these architecture changes are obvious. With a disaggregated architecture, computing nodes and storage nodes can be scaled separately. On computing node, we can support flexible resource configuration from low end with 1 quad core and half gigabytes memory, all the way up to 96 cores and 768 gigabytes memory. The maximum data size is 1 petabytes and up to 15 read-only nodes in one single cluster. Together with other optimizations, the read and write performance is significantly improved. In our experiment, we can say 1 million QPS for read and 500,000 QPS for write. Also, for the failover and snapshot of backup, this operation can complete in a few seconds. Most important, it makes it easier to implement very important feature, serverless, which we will discuss with more details later. Okay, so let's start with let's discuss the key technologies we implemented for TT-SQL C. There are two parts. One is the serverless features, and one is the performance optimizations. The first serverless feature is computing storage. Actually, decoupling storage layer from computing layer is the first step for elasticity and serverless. We implement some database logic at the storage layer to deal with the offloaded read log. On the left side of the picture, the first 3 steps are synchronized operation. The computing layer only needs to confirm the log persistence at the storage layer, and then the storage layer takes care of the rest of everything asynchronously at the background. On the storage node, data and logs are organized inside a cell. There are 3 replicas for each cell for availability purpose. We also maintain multiple versions of data page, just in case we need to read the old data. The old version of pages and logs can be recycled whenever it's required. For example, when the storage space is almost exhausted, the recycling operation will be triggered automatically. Each cell replaces the read log to change the data page and also persist the new version to the disk. This operation can be performed in parallel across different cells. In order to make it happen, the redo log is fragmented to small pieces according to the page it belongs to. The system will dispatch the redo log to specific cells so that the redo replay can be done in parallel. The other interesting feature we bring the value to customer is that the customer only need to pay the resource they are exactly using. In the past, the size of data file keeps increasing as the rows are inserted to the table. However, the occupied size won't go down, even though the data are deleted later. The real size of the data file is essentially reduced, but they still need to pay the large size of the data. As a result, the customer will definitely complain for the unused resource. In order to make accurate calculation for the space usage, we can rely on 3 different lists that are associated with one segment. They are full extended list, not full extended list, and free extended list, respectively. Only the extend in the full list and the partial full list are added up for the space usage calculation, which can help the customer to save money. Furthermore, if we think the storage layer as a resource pool, we can managing the allocation and deallocation unit inside of maybe 1 megabytes, and whenever the extend is not be used anymore, we can release them to the resource pool, so that the unused extend can be used for some other purpose. So in order to achieve faster elasticity, we need to make sure the computing node can be able to shut down and start up instantly, so that we can quickly adjust the computation resource. For startup process, we optimize the buffer pool and the rollback segment initialization process by making them runs in parallel. As mentioned in the previous slides, recover process can also be done on multiple cells in parallel, which is also very helpful for the faster startup. We also rely on the shared memory for the buffer pool, so that the lifetime of buffer pool is independent from the database instance. The data in the shared memory buffer pool is still warm even after an instance is rebooted, which shorten the startup and the recovery time. As indicated by the orange curve in the figure, after the instance reboot, the system throughput restores to the peak status shortly after it's rebooted, and no performance regression is observed right now. Compared with the regular instance, it takes longer time to warm up the buffer pool before the peak throughput can be reached. This can be indicated by the blue line. As for the shutdown process, since there is no dirty page flash on the computing layer, it's pretty safe to shut down the server right after the redo log is persistent on the storage layer. Okay, let's take a look at some performance optimization features. We introduced a very important feature called secondary cache in our storage architecture. Before, we made a lot of efforts to optimize the read performance and the write performance, like using the log-free data structure and to make the asynchronized group commit and try to make the workflow pipeline and batching. But actually, the overhead from the notebook I/O cannot be ignored. Originally, there are only 2 layers in the storage hierarchy, where the memory is always the first priority for caching the frequently accessed data. When the cache is full and a cache miss happens, we have to rely on remote I/O to retrieve the data and select one entries from the cache to replace with the new one. In the TD-SQL-C, we implemented the secondary cache layer in between memory and the remote storage. It's backed up by the host's local disk. The page eliminated from buffer pool are cached at this layer. When cache miss happens, the secondary cache layer is checked before making a remote I/O. For performance purpose, we can use the SSD or the NVMe storage device as the media for the secondary cache. Some small amount of memory is required to maintain the metadata of the secondary cache. For example, the hash table to keep the page ID mapping, the free list to maintain the free spaces at the secondary cache. This metadata is pretty lightweight in memory, which only occupy the space of about 1/256 of the data size in the secondary cache. Further optimization, including skipping double writes and bypassing the file system. SPGK API is used for devices like Open and OEP. In our experiments, when configuring the secondary cache with a size 5 times as large as buffer pool, the read workload performance is improved by more than 100%. This work is inspired by the accepted paper of this year's Sigma, and our team makes contributions on this paper. And also, backup and restore is very important to ensure the data security. Thanks to the architecture advantage, we can also do very fast backup and restore that are completed at the storage layer. The computing layer is even not aware of this operation. The backup and restore can be done at each cell in parallel. We have a mechanism to ensure that a global snapshot can be made for the backup. In our experiment, the backup only takes a few seconds to finish, and the data can be restored at the gigabytes level speed, which is pretty fast. Okay, with all of this architecture change and optimizations, we can say the GTSQL-C experienced a very fast growth since its release. The year-over-year increase in terms of the number of instances during the past 12 months is almost 34 times. GTSQL-C is adapted by many customers from different areas, including e-commerce, finance, videos, and so on. So the current result is pretty promising and encouraging. But of course, we still have a lot of things to do and have a long way to go, since we will definitely meet a lot of challenges in front. So let's talk about the challenges in front and our future work. Going forward, the evolution direction of the database technologies will continue to be defined by the business-driven requirements. For example, the e-commerce and the games industry requires extremely performance. To meet this requirement, maybe we can rely on some technologies like the multi-write for the high write throughput, and hardware acceleration can also be considered at the storage layer to speed up the I/O. For the finance and government applications, where the high availability and the security is more concerned, we can develop features like the SQL audit, the database encryption, and the global database. The global database can provide cross-AZ availability and the data locality. In the IaaS and the SaaS area, maybe it involves a lot of hybrid workload. In order to resolve that, maybe we have to do something like HTTP and in-memory processing. And maybe we have to adapt some external ecosystem to support different workload. and we can also consider something like the cold and warm data separation. So later on, I will roughly introduce some technologies we just want to explore. One is the multi-market. So far, we made a lot of efforts on scaling read throughput, but the problem of single point write is still there, which could be a system bottleneck in some case. We have some mature ideas that are being explored and investigated. For example, the dedicated log server to globally deal with the log-related logic, like the data consistencies. In that sense, the existing log transferring between the master node and the save node will not be needed anymore. Meanwhile, we can rely on the logical partitioning concept for non-conflicting multi-point writes. The data at the storage layer may or may not be physically partitioned. I think this is a pretty challenging project with more details to make sure. HTTP is another popular topic right now. The traditional T+1 solution connecting a TP system with an AP system through the ETL channel might not be the good solution for some real-time applications. Many products are building HTTP functionality. We also create a system, a columnar-based engine to speed up the analytical queries. On the left side is our current solution, where the system is deployed as an individual RO node. Whether a query should be executed in the row-based engine or column-based engine is totally determined by the proxy through the manually specified connection string or some very simple heuristic rules, which in many cases may cause some incorrect query routing. The other problem with this solution is that the entire query has to be processed on either the row-based engine or the column-based engine. It cannot combine the advantages of both engines. So in order to support the fine-grained query planning, we need to build a columnar engine into the MySQL instances as an enhancement to the physical operation in the query tree. The optimizer will determine which part of the plan should be offloaded to the columnar engine and where the intermediate columnar data should be materialized to the row format. Finally, we will talk about the computing storage extension. Originally, we implemented some database logic in the storage layer, which is redo log replay. But we can do something more because one benefit is that we can take advantage of less use the CPU resource on the storage layer. The idea is that for some rows that are not qualified for the predicates condition, we can try to fill out them before sending back to the computing layer. This requires to extend the computing storage functionality to support the filter pushdown. Maybe we can also support aggregation operations as well. So in order to make that, we need to implement the internal protocol to exchange the SQL query plan operations to the storage layer, and also the storage layer send back the intermediate result back to the computing layer. There are still a lot of work involved in this project as well. Okay, it's the end of my talk. Thank you for listening. Any question, please feel free to contact me and our team. Thank you.